All right. So today we're going to continue off of stability, and we'll probably finish up stability because we'll be skipping the bulk of this chapter, and then we're going to go straight to chapter 7, which is states steady state errors. The main reason why we're skipping most of stability is because we're skipping Routh-Hurwitz criterion. We're just going to go over some formal definitions on stability. And the biggest thing that you have to take away with the stability in this class, until chapter 10, is that your eigenvalues are negative, your system's stable. Your eigenvalues, if you have a pair of imaginary eigenvalues, you have a marginally stable system, and if you have one positive pole or more, then you have a unstable system. We'll be classifying specific definitions of stability as well in this chapter, but then the Routh-Hurwitz criterion is outdated and it's not useful because it doesn't account for system with delays. So let's say if I put an input into the system, then there's a 50 millisecond delay or 100 millisecond delay before the system reacts to it. That delay could cause instability even though you have all negative eigenvalues. So it's not very useful when it comes to delays, and all discrete time systems will have delays. Even though we'll finish chapter 6 and start chapter 7, and it seems like we're really far ahead, chapters 8 through 10 are very heavy chapters. Each chapter will take over a week to cover, and they're probably the most important parts of this class, especially chapter 10. So that's why I'm trying to get to chapter 10 as soon as possible, because it's probably going to be the most useful chapter for your future controls classes and even in application and industry, because we usually look stuff in the frequency domain. Any questions? Homework 2 solutions haven't posted. I forgot to post it last weekend, and I'll post homework 3 solutions by Saturday, so that way you can go over it, or I'll post it by end of the day Friday, so you can go over it, because homework 3 will help you out with the midterm as well in terms of material. Midterm 1 from last year, the solutions will be available tomorrow as well, so please go over it. If you do well on this last year's midterm, then you should generally feel good about the actual midterm for this year. The best, I guess, immersion would be to take it under the time constraint that last year's students have, which is roughly 55 minutes. So if you can finish it in 55 minutes, so you're set. Just a hint for last year's midterm, you can solve it without a calculator if you can factorize whole numbers. Usually for factorization, it'll be in integers for midterm 1. Yeah. And you can still use a calculator, because if there is going to be calculation, it'll be just very basic multiplication and division. Okay, so chapter 6, we're going to talk about stability. So yesterday we started with some definitions. We talked about the 3 main goals of controller design focus, and we also talked about the total response. Again, that it's the total response is force plus natural, and basically what it means for stable, a system is stable. If we just generically say something is stable, that means the natural response goes to 0 as time goes to infinity. So a system is marginally stable if the natural response remains constant or oscillates and is bounded. And a system is unstable if the natural response approaches infinity as time goes to infinity, meaning that the output is unbounded. And this is all based off of the definition. These definitions are all based off of the definition of a natural response, meaning this is based off of the initial condition. So if your initial condition isn't adding energy, but your output becomes unbounded, that's unstable because yeah, that's just the definition of it. Now, this is one set of definitions focused on the natural response. I think this is a better, more comprehensive definition for stability, where you have something called bounded input, bounded output stability. And this accounts for the total response. So a system is bounded input, bounded output stable if every bounded input yields a bounded output. And this is the exact definition from the textbook. So as an example, if I have a step input is a constant input, meaning it's bounded to that value, that final value. And if my output is also bounded, then this is bounded input, bounded output stable. Bounded input, bounded output unstable means a system is unstable if the output is unbounded for a bounded input. And this definition means that if you have any kind of input that is bounded and the output becomes unbounded, then that is unstable. Bounded input, bounded output, unstable. And this is based off of the total response. So this accounts for the input. So one question I want to ask you, and maybe it's not fair, but let's if I have an output response that is marginally stable, like this, and I'll give you context. So this is my output response for a system that's oscillating and bounded right here. And so let's say this is a spring of some sort that is not losing energy and it's oscillating up and down and at some frequency omega. And if I were to take the Fourier transform of this of the system, we'll see like a peak right here at omega at some value, like a Fourier transform like that. It's flat everywhere else. Is this system, and so this is marginally stable. We know that this is marginally stable. Maybe instead of asking, is this bounded input, bounded output stable, is there a condition where I can make this thing oscillate bigger? Have you ever tried, have you ever experienced resonance before, where something just keeps growing and growing? But then how do you get resonance? So yeah, so you have an input that matches the frequency, then you're adding energy at that frequency. So resonance will make this go unstable if you have no way of, yeah, so the Tacoma Bridge is an example of that as well, where it's marginally stable, but then resonance makes it become unstable as it oscillates bigger and bigger. So this is actually bounded input, bounded output, unstable. The reason why is because my input, if I put input at this frequency, it's going to grow on the output side. So even though the input's bounded, the output becomes unbounded. Now, in the case of the Tacoma Bridge, where it's like a constant wind gust, the thing about a constant input, like a step input or impulse input, is that the input excites all frequency ranges. So it's also exciting that specific frequency as well, while all the other frequencies are not excited, that frequency is still excited. So it's like hitting something with a hammer. If you hit a tuning fork, you hit it, it vibrates at that frequency because hitting it with an impulse still excites all frequencies. So if you constantly hit something with a hammer, it's going to be exciting that frequency. It's going to have resonance, going to grow unstable. So marginally stable systems are actually bounded input, bounded output, unstable. So if you actually have a set of so let's say my input, like my output response is like y of s is equal to like so this is my numerator term, and then maybe in my denominator term I have a pair of complex conjugate poles. So I have plus j omega and s minus j omega. But this is my output response. So then my input is also a sine response as well. Then I have a sine input of see what's the it'll be it'll be s squared plus omega squared, right? Doesn't matter if it's sine or cosine, but that's my input. So this is my input. This is my transfer function. And let's do different colors to highlight poles. So then I'm gonna have a pair of complex conjugate poles here. This is the pole zero map. And then I'm gonna have a second pair from the input here as well. So then what's happening is that the second pair of poles from the input is actually exciting. It's going to cause the system to grow unbounded. When we look at the response, it's going to grow unbounded, and this is what causes resonance. So when you have a pair of complex conjugate, or if you have a pair of conjugate poles, and then you have a second pair of conjugate poles at the same location on the imaginary axis, then that system's going to grow unbounded. Maybe I'll write this causes resonance. Causes resonance. Output grows unbounded. So that's basically what I want to go over in chapter 6. There's a few tricks I want to provide you as well for determining. Do you have a question? Sorry. Oh, I just saw a hand wave. So, yeah. So, just a few, I guess, points to make. A system is stable if all the closed loop poles are in the left half plane. And when I say closed loop poles, this is going to be a system with feedback. So I'm going to be talking about specifically this system here. And one thing I want to talk about is the difference between closed loop and open loop poles. So the closed loop transfer function, usually in the textbook, we denote it as T of S, and sometimes we'll write CLTF for closed loop transfer function. We denote it as T of S, which is going to be equal to G over 1 plus GH. So then the closed loop poles, are going to be values of 1 plus g of s, h of s is equal to 0. So those are the closed loop poles. So we're talking about this term here. Now, when we're talking about open loop poles, it's going to be g of s is times h of s is equal to 0. So these are open loop poles. And you can have unstable open loop poles, but then once you close the loop, you can have a stable total system. So this is specifically with systems that have a closed loop. If I just have a system that is like this, there are no closed loop poles. They're just poles. And then you just check the poles of G. So if I give you a system with feedback, you need to check the closed loop poles for stability. If I give you a plain system like this, you can just check the poles of G. If I ask for the open loop poles, be sure to include the H as well, because the definition of open loop system is G times H. So I'm going to write right here, open loop transfer function, you denote it as OLTF, is going to be equal to G of S multiplied by H of S. Sometimes you'll see just G alone because we're talking about unity feedback where H is equal to 1, but this is the actual definition where G of S multiplied by H of S is the open loop transfer function. And we include the H because that's the sensor and that's our output reading. Yeah, question.
H is not in the diagram.
In the open loop diagram? Oh, like right here. Oh, this is just a generic transfer function. Maybe I can call this f of s. This is just some generic transfer function. It can just be g of s multiplied by h of s if you want to see that, but think of this as just a open loop system, not a open loop transfer or open loop transfer function. These two definitions are tied together with these two are tied together for feedback system. So I would think of an open loop transfer function and a feedback system as G times H. And then closed loop transfer function is the equivalent block diagram of the whole feedback system simplified to one block. That's the closed loop transfer function. But then here, this is just a open loop system because there is no feedback. So like, I guess you can start interchanging it, but use the block diagrams as context of what to check for stability. Maybe I'll just call this K of S. K of S is an open loop system. This is so I'll say pertains to feedback systems. Okay, so I guess that goes back to earlier I said that a system is marginally stable if there exists a conjugate pair of imaginary poles. And then a system is unstable if there exists at least one pole in the right half plane. So that also makes a bounded input, bounded output unstable. So I just like this visual. So if I have a imaginary axis, I have the complex plane here, real axis, and this is my pole zero map. I would think of this whole range here as stable. And then I'm going to draw like a hard border here, where maybe this is like some tiny border that is infinitesimally small. Stable and also bounded input, bounded output stable. This imaginary axis is our border for marginally stable. It's also, and then this red side here is unstable. And to drive home the point, anything on the imaginary axis in right is also bounded input, bounded output, unstable. Perhaps I'll just do a different color. Yeah, I'll do blue. All right. So now I think the most useful part of this chapter, besides the definitions, well, at least the most useful tools now is evaluating stability without calculator here. So when we look at the poles, we're looking at the denominator terms. If you notice that there's at least one sign change in the closed loop denominator, the system is unstable because there must be at least one positive and one negative eigenvalue. So like if I have, like s squared minus 4s, oh, yeah, minus 4s plus 4, then we get s minus 2 squared, meaning that we have a two positive poles. Now, one thing I want to make a note is let's say if I do have and we don't care about the numerator term, but let's say we have like uh something like that. Just because everything is negative in the denominator doesn't mean it's unstable. You can just pull the negative out and put it in the numerator, and you get and that's fine. Could be stable, could be unstable. I don't know actually because there's no sign change. So this goes both ways. If it's all negative or if it's all positive, then you still don't know if it's unstable. But if you see one sign change within the denominator terms, then the system is guaranteed unstable. Now, if you're missing a power of in the denominator, like a power of s is missing in the denominator, the system is either marginally stable or unstable. So missing a power automatically guarantees that your system is now bounded input, bounded output, unstable, or at best, marginally stable. So the example is this, s squared plus 4. We have roots at plus or minus 2j. But then if you have s squared minus 1, we have a sign change, and we also have a pole at plus or minus 1. Now, what 2 implies as well, condition 2 implies that the poles are symmetric. There's at least a pair of poles that a pair of poles are symmetric about the origin. So what that means is symmetry about the origin means you can have symmetry about the real axis where we have pole like that. So like the s squared minus 1. So you have a plus or minus 1 symmetry at the or symmetry on the imaginary axis. You could have symmetry about the real axis. So this is where you have that pair of imaginary poles. Oh, here, change that here. Or you have symmetry about the real and imaginary axis. And I don't remember what the word is called. It's called quadrantal or something. I don't remember the term for it, but basically you have symmetry about the real and imaginary axis where you have this. So symmetry on the real axis. And then you have symmetry on the real and imaginary axis. So if I label this A, B, and C, B is our best case scenario. Because at best we can do now is marginally stable system. A and C will automatically guarantee that our system is unstable. So the odds are kind of stacked against you right here if you have a missing power of S. Now, if all coefficients of the denominator are the same sign and are not missing a power of S, there is no definitive location on the pole location. So this denominator here, S to the fifth plus 3s to the fourth plus s cubed plus 2s squared plus 3s plus 1 has a pole in the right half plane. I don't actually have it written down, but there's going to be there's one pole in the right half plane. All right, so usually we hope for either case 1 or 2 on homework and exams. Case 3 is usually what you'll see though, where there's no missing powers and there's no sign changes. But this is still a helpful trick for you to immediately tell if a system is stable or unstable. Usually I just look for sign changes. And then if I see a missing power of S as well, then I know that we have symmetry. One thing that doesn't count for 2 is, let's say I have this system s cubed plus s squared plus s. That doesn't count because you can just pull this out as s squared plus s plus 1. This does not count because it's not missing a power of s. All right, so these are some useful tools for determining stability. Are there any questions? All right, so moving on to Routh-Hurwitz, we're skipping it. So happy I don't have to teach it this year. I don't like it. If you are dying of curiosity, email me. I can post the lectures from last year along with the lecture notes for Routh-Hurwitz criterion. You'll never use it outside of this class, but if you're dying of curiosity, um, it's a way of determining basically the something you use the Routh-Hurwitz criterion as a way of determining the number of closed loop poles on the left half plane, right half plane, and imaginary axis, but you don't know the exact location. You just know how many poles are in each of these sectors. It's useful for determining stability by hand. It's not useful. It's not useful at all. Yeah. Anyway, one thing I will want to say though, something that I read in literature and you'll hear in other classes, one note to say about Routh-Hurwitz, or at least with this guy named Hurwitz, if someone says, so the A matrix from state space, if someone says A is Hurwitz, this implies that A is bounded in that this implies that A is stable. I wouldn't go as far as saying bounded input, bounded output stable, but it just says A is stable, meaning that all eigenvalues of A are negative. There are no purely imaginary eigenvalues. All of them have negative real parts. So you'll hear the saying if they say the system is Hurwitz or A is Hurwitz, or like if they say the system is Hurwitz as well. So maybe this is something you will read in literature. It's just a saying. I don't know why they don't just say A is stable or the system is stable. They like to say the system is Hurwitz, maybe to sound smart at conferences. Don't know. Something I've noticed. So that's just a saying. They don't say A is Routh-Hurwitz. They just say A is Hurwitz. So yeah, the Routh-Hurwitz, you make this table, then you find the determinant in each column, and then look for sign changes. Don't care. Special cases, don't care. Skip this. Oh yeah. All right. Straight to the end. Stability in state space. What did I have there? Wow, we're going so fast. Stability in state space. You can determine stability of the system with the A matrix. Oh, yeah. So I guess this is something that I mentioned in the earlier chapter. Uh, you only need to find the eigenvalues of A. B, C, and D do not matter in your for stability. So once I give you state space and tell you to find the stability, you don't even need to apply B, C, and D. Just find the determinant of SI minus A is equal to 0. And you solve for that, then you can determine if their system is stable or unstable based off of the values of the eigenvalues. And make sure that this A is of your closed loop transfer function. Usually though, it's pretty easy to discern, or I'll give you the closed loop transfer function for A. Okay. Takeaways: the system stability is based on the location of the closed loop poles. All closed loop poles in the left half plane means that your system is stable, and also bounded input, bounded output stable. Minimum one closed loop pole. If there's at least one closed loop pole in the right half plane, that means your system is unstable, and it's also bounded input, bounded output unstable. If there's at least a pair of unique conjugate imaginary poles on the imaginary axis, this means it's marginally stable. But if you have two pairs that are not unique, that means they overlap with each other, it actually becomes unstable as well, and bounded input, bounded output unstable. And we can determine the number of closed loop poles in the, well, we don't care about this point. I mean, it's true. I won't cross out. It's true, but won't be tested, won't be on the exams, won't be on the final. We're skipping it. All right. That's chapter 6. It's amazing. We're on to chapter 7. Maybe I can start teaching you guys 547 if we finish early. No, I won't. So chapter 7 is going to be on steady state errors. And basically the purpose of this chapter is to learn what conditions causes a system to have error at steady state. I would say that the equations in this chapter aren't too useful outside of this class, but it's useful learning how to derive error for each system because every system you might have different systems that are not standard configuration where you have a system with a single feedback. Maybe you'll have a system with multiple feedbacks. Maybe it's like a system that looks like this, where you have a feedback here, you have a feedback here, and then maybe you have a feedback here, block here, maybe a block here, block here. So then learning how to derive error for this particular system will be useful, but we can't use the equations from this textbook on that kind of system. So, yeah, this is just like a generalized, I guess this is just more of a, think of it as a tool, like your analysis develop in this chapter will be a tool for systems that are not standard. We're going to be going through just basically the definition of test inputs, followed by steady state error for unity and non-unity feedback systems. Unity meaning that H, our sensor, is equal to 1. Non-unity feedback meaning our sensor is no longer equal to 1. It's some transfer function as well. Then steady state error for disturbances. So now if we have a disturbance source, so we have multiple inputs now. We have our test input and we have a disturbance coming in. What do we do then? And then steady state errors for state space systems. So how to determine steady state error if I give you a state space representation. So we're going to go through the introduction first with just the definitions. Going back to the requirements for control design. So think of transient response that we covered in chapters 2 through 4. And then we just talked about stability. Now we're going to be focusing on steady state errors. Our goal here is when we have a controller design, maybe we want to reduce steady state error. Maybe we want to make it 0. Maybe we want to make steady state error bounded. Sometimes steady state error can grow unbounded, and that's not good. So this design of controllers is to focus on controlling steady state errors as well. So the steady state error is defined as the difference between the input and output for a prescribed test input as t goes to infinity. So this implies that we look at steady state error when the transient response goes away. Basically, I mean, it's implied it's at steady state. We look at the error once the transient response goes away. And here's the block diagram. So steady state error exists only for stable systems because if our system is unstable, then our output grows unbounded, our input is bounded, error grows to infinity. Here, steady state error is defined based off of this junction here, where my error in the frequency domain is equal to my desired input minus the output signal multiplied by the sensor. And note that this only applies for negative feedback. It wouldn't really make sense to have a reference input and then add our output to it. That doesn't tell us much. It makes more sense to say we have a desired input. This is what our output is actually at and see what the difference is. That's our error. Just to really drive in the point, when h of s is equal to 1, this is called negative unity feedback. And negative non-unity feedback means that h of s is not equal to 1. All right, steady state error is defined as this. So ESS here is in the time domain. As limit of t going to infinity of e of t, which is equal to the limit as s goes to 0 of s times e of s. And this definition comes from, it's called the final value theorem. And usually we denote it as FVT. This is from table 2.2, property number 12 on your Laplace transform tables or your Laplace transform table properties. It's called the final value theorem. So basically, you can actually find the value of a system at time equal to infinity by taking this definition here. This is also useful for finding useful for finding the DC gain when you have a transfer function. Because if I have a g of s, I apply the final value theorem of g of s multiplied by the test input, which is 1 over s, which is a step input. And a step input has a unit input magnitude of 1. Then my output, whatever value it is, that's the gain of the system. And you apply it. So this is useful for finding the DC gain. Little side note. So we use test inputs at Unity to determine error. And we assume that for anything that is a negative time, when time is less than 0, that our test input is 0. So these are our test inputs. We have our unit step, which is, these are the definitions, a unit ramp, which is linear with time, and then you have a unit parabola, which is a parabolic with respect to time. And these are the respective definitions in the frequency domain. So steady state error can be 0, constant, or infinite. The way we define it is this. If we have, let's say, a test input, step input. This is our step input. And specifically unit step input. And let's look at our output. It looks like this. Flattens out right here. We ignore the transient response. This is the transient part. So we want to take a look at steady state. And this difference here is my steady error at steady state, which is equal to E at infinite time equal to infinity, which is constant. So if I were to have a ramp input, And my ramp input is linear with respect to time. We might want to have something that looks like this. As long as it's parallel here, we're good. But the minute we have a line that's not parallel, kind of like that, where the line is off even just a little bit, then this system has an error that will grow to infinity. Well, maybe here we measure these 2 points here. This error here is still constant. So the textbook says that steady state errors come from your system configuration and input type. So one example is nonlinearities in system like gear backlash. So when the gear moves, the amount of wiggle between each gear can cause backlash, and that's a nonlinearity that is not accounted for, and that's a source of error. When they talk about input type, there's also something called system type. It's dependent on the number of open loop holes you have at the origin. And we'll talk more about that next class. But basically, when you look at the open loop transfer function, you can tell if the system will have if it will have steady state error for a constant, for a not constant, for a test input. Based depending on the type of test input it has, you can tell if the system will have steady state error. So we'll cover that next class. On Thursday, I will do a review of the midterm material, so chapters 1 through 5, and go over, I guess, the key concepts from each chapter. All right, thank you.